good morning to all of you. So for a few minutes, please go through whatever we did in the last class, and you can ask any doubts, questions. Actually, it cannot be lumped the way we can do the mass matrix, but through the transformation of the degrees of freedom, say in the modal space, you can transform the equation of motion into an uncoupled system of equations. But not as it is, the way we are for the mass matrix we are diagonalizing. In the same degrees of freedom space, you can't diagonalize the stiffness matrix. Then that will not give you the correct estimate of restoring forces. It's like the spring, so the spring force depends on the relative difference of the stretches and the displacement of the two ends of the spring. So you cannot convert that equation in terms of a single displacement. So that's how, yeah. Yeah, so here what we are saying is that U1 is 0 at all time instances. So if that is not the case, then it would be more like initial condition on U1 or its first and second derivatives. May not be the valid condition at all time instances. So that would go as in the form of initial conditions. Maybe I'll repeat this last question for everybody. So okay, are there any questions? So see, there were two questions. One was about the way we discussed the diagonalization of mass matrix. So if you use lumped mass matrix, you can diagonalize it. And so for example, in central difference, you don't have to solve set of simultaneous equations. No matrix inversion or no solution of simultaneous equation is involved. But whether the similar thing can be done for stiffness matrix, so that was the question. So see, you cannot lump the stiffness matrix. In the sense, no diagonal lumped form of the stiffness matrix cannot be derived. Of course, if we transform the nodal degrees of freedom into another set of coordinates, typically what is known as modal coordinate space. So through the modal transformation, then you have the governing equation in modal space, pre-vibration mode safe space. There you can have a diagonal, basically uncoupled system of equations. But in this same no degrees of freedom vectors, you cannot diagonalize stiffness matrix. So maybe because the restoring forces are usually dependent on the relative displacement between 2 points, unlike the inertia force, which you can say typically in a lumped system, inertia force at a mass depends on the acceleration of that mass. But as far as the restoring force is dependent, it depends on the relative displacement between 2 points. So if you, for example, take 2 ends of a spring, so say if this has some displacement, let us say U1, and this has a displacement U2, then the force experienced by the spring is dependent on the difference of these two, not just one of these. So I cannot write that force simply either in terms of U2 or in terms of U1. So the stiffness matrix cannot be in the elemental degrees of in the usual degrees of freedom vector space, cannot be diagonalized, cannot be lumped to a diagonal stiffness matrix. So that is why we were only emphasizing on mass matrix. And then the second question was, in the last class also we had considered of this problem in terms of I said boundary conditions. So what I was saying that in this particular problem, that this end is fixed, and here we had actually a spring. So and then we had said that this is node 1, of course this is node 2, and this is node 3. So here, since U1 is 0 at all time instances. So when we are saying boundary condition, the boundary condition is true at all time instances. So this u1 t is 0 at all time instances. If I plot u1 versus time, it is 0 at every time instant. And that is why, you know, when you differentiate it, since it is 0 at all time instances, so its derivative will also be 0 and its second derivative will also be equal to 0. So that is how we had, based on this, we had written this condition. But then the question was, there can there be a possibility for this is 0 but no u1 double dot, let's say, is not 0. So if this is 0 at all time instances, then this will always be the case. But suppose no, this is 0 at only t equal to 0 initially, and then it's possible that this may not be 0. So then that's a kind of an initial condition, that u1 is 0 at only t equal to 0, subsequently it is not 0. So then that would go as an initial condition, not as a boundary condition. So then we can't know, since u1 is not 0 at all time instances, so therefore this acceleration or these first derivatives will also be non-zero, you know, subsequently. So are there any other questions? It depends. So see, if usually if the problem is a linear, and that is what we have been discussing in this course, so then they are formed only once. Yeah, and then you basically continue the solution using the same mass and stiffness matrices. Maybe your load vector is changing with time, the right hand side, because of changing velocity, acceleration, displacement, and also the forcing function. But in case of nonlinear problems, which we have not discussed in this course, you will have stiffness matrix which is dependent on the solution itself. So then that has to be updated every time. Even there can be inertia nonlinearities, then the mass matrix would also be dependent on the solution of the problem itself, and then therefore in that case it has to be updated every time. So but for linear problems, yes, the mass and stiffness matrices are there actually updated once, and then you continue to use that same thing for subsequent time steps. Yeah, are there any other questions? So then let me continue. So the last class, what we were discussing is the central difference. So there are two more points to be discussed in this central difference technique for integrating the equations of motion technique. So what we had said in the last class, that finally if we look at the equation, I think the last class whatever equation I had written, so the final form of the equation we had written as 1 by delta t square into m plus 1 upon 2 delta t into c, and then this is d at t plus delta t is equal to, right hand side we had this force vector at time instant t. We are considering the equation of motion at time t to find the solution d at t plus delta t, minus we had m, and then into minus 2 by delta t square into d at t, and then we had plus d at t minus delta t. The last class whatever equation I had written. So this was one term, and then plus we had 1 upon delta t, sorry 2 delta t I think, okay, into c into d at t minus delta t. So this is the general final form of the central difference scheme I had written. And what basically we are trying to do here, if we look at in the time march, this is what is known as time marching. So we start at t equal to 0 with the given initial condition, and then we obtain the solution at delta t, then at 2 delta t, and so on. Maybe somewhere here t minus delta t, then t, and t plus delta t, and we continue that. So this is what we are doing. Starting from here, we get the solution here, then here, maybe some instant here, then next here, and we continue like that. So now in this process, if you look at here in this equation, when you are trying to find the solution at delta t, so in the, to get the solution, that means I want get d at delta t, means t equal to 0. So now this is a known point, and then you want to find out the solution for this point. So if you put t equal to 0, you will find on the right hand side You will have of course f evaluated at 0, that is at t equal to 0, d at t equal to 0, which will come from initial condition, but you have one more term d at minus delta t. So that means you are going on this side and you are saying that no, you also need here d at minus delta t, which is not known because we are starting with an initial condition, that is at t equal to 0. So then what do we do? So we actually, in terms of these initial conditions, so that if you look at the expressions for velocity and acceleration at any time t, so if we write the same thing at this t equal to 0, so I can say d dot at t equal to 0, same central difference formula which we had written in the last class. So I can say that this would be d at delta t minus d at minus delta t divided by 2 delta t, isn't it? I can write the velocity here using central difference, and this is known because we know the initial condition. So d naught dot will be known to us. So I can write that as this value of displacement at this point minus value of displacement at this point. So, and in which of course I have this as a known quantity, and both of these are unknown. This is unknown, this is also an unknown, because we don't know before t equal to 0 what is the displacement vector. Our starting point is this. So same way I can write the acceleration at t equal to 0, that is d double dot naught is equal to, using the same formula which we did in the last class, del t square, and then this was basically d at t plus delta t. So this would be dt minus 2, this would be d naught, and then plus you will have d at minus delta t using the same formula. So this is your d naught double dot. See, in these two equations, if you look at, we know this from the initial condition, we know this from the initial condition, because we know starting point, what is the initial configuration of the structure, if there is any initial velocity given or not. And then from the equation of motion at t equal to 0, I will also be able to find out this d naught double dot, because if I look at the equation equation of motion m into d naught double dot plus c damping forces d naught dot and plus k into d naught is equal to value of f at t equal to 0. So from this equation, from the initial condition, we have to have these and this. So, and this is anyway the known force, so you just put t equal to 0. From this you can find out d naught. So that is, take these two terms to the right hand side, multiplied by m inverse will give you d naught double dot. So this you can get from here. So once you have got this, so that means in these two equations, that is this equation and this equation, for the velocity vector and acceleration vector at t equal to 0, I have this known quantity, I have this as a known quantity, I have this as a known quantity. So what are the unknowns? Unknowns are this d at t plus delta t and d at minus delta t. But what we want is this, anyway we are going to solve from this equation, considering the equation of motion d at delta t, but d at minus delta t we need to start this central difference scheme here. So you can solve these two equations. So now the solution of these two equations will give you finally, you can eliminate d at delta t, and you can write the, you can just write that solution. So what you want is just solve for this d at minus delta t. So you will find that solution, you can just look at the steps involved. So we straight away you have to eliminate this d at t plus d at delta t. So you will find that this solution will come out as delta t square into d double dot naught and minus by 2 and minus delta t into d dot naught and plus d naught. So this will be the expression for d at minus delta t. Actually, if you look at, this is more like a simple mechanics equations of motion you would have done. S is equal to ut plus half at square. So it's like that. So this is like half at square. So this t here is delta t, because we are trying to find out the solution here. That is kind of displacement here. So that is delta t. T is delta t. So delta t square by 2 into acceleration, and then you have plus ut. And since t here is minus delta t, so you get minus delta t into velocity is initial velocity vector is d naught dot. That is initial means starting point. and plus of course you have some displacement here. So finally you see that this equation comes out like that. So one can directly write this, but actually comes from the solution of these two equations. So from this equation now we can work out d at minus delta t. Once we have this, and then now we can work out the solution at no delta t from this equation, and once we have got the solution here, then we can go to 2 delta t, 3 delta t and so on. So then that is how you continue. So this is one starting initially at the starting point, you need to actually just evaluate this quantity in case of central difference scheme. And another issue here is actually stability. So that's true for all the explicit integration techniques. Whenever you use explicit techniques, so there is always a stability issue. That stability means you will get the accurate solution, not accurate but stable solution. So stable solution only if, I will tell you what is the meaning of stable. So stable solution if delta t, whatever this delta t we are choosing, this time discretization, because we want to choose certain delta t, and that delta t has to be delta t must be less than equal to certain critical value. So here in case of all explicit integration techniques, you need your delta to be smaller than this delta t critical, then only it gives you a stable solution. A stable solution means what? That actually maybe I have a structure and it is having certain boundary condition, and then there are forces, and the forces are functions of time, say some qt and so on. And then when you are trying to solve, we know that under whatever loading condition this structure is there. So if I look at the displacement at some point, let us say here some displacement w versus time, so I know that when I continue integrating the equation of motion, the solution is going to be bounded. It can have multiple frequency component, I am just trying to illustrate you. So this here input is bounded, that is this force is not infinitely going to increase with time. So input is bounded. Bounded means it is within certain limits, so it is not infinitely increasing, and output is, so then we expect here for this problem that the output is also going to be bounded. Now what happens if your scheme is unstable? If numerical scheme is unstable, so even though you have the expect the solution to be bounded, so that is input is bounded, expected output is the output is expected to be bounded, output is, that is what we expect. So output is expected to be bounded, but actual solution, whatever numerical solution, actual numerical solution, numerical means whatever we are getting, actual meaning is that whatever we get from an unstable numerical scheme. So but actual numerical solution is unbounded. Unbounded meaning is that actually we were expecting the solution to be like this, but we are using unstable numerical scheme. So for example, in this case you are using delta t larger than this. So if you are using larger delta t, maybe initially it might follow this, and then finally it may blow like that. So it might actually keep on increasing. So what it does is actually magnifies the whatever errors are there in the solution, because this is a numerical solution, will always have some round off errors, truncation errors, and those errors keep on magnifying if you are using an unstable numerical integration scheme. And in this case the central difference, if delta t is greater than this, is going to be an unstable numerical scheme. So this is the limitation, that we need to use this delta t less than this delta t critical, and typically this delta t critical is essentially governed by what is the smallest time period of this system under consideration. Like I was saying that we are talking of a structural system, it's an infinite degrees of freedom system, will have infinite number of frequencies. So if you consider the highest frequency, now of course that infinite degree of freedom system, infinite element we are converting into a finite degree of freedom system. So we have finite number of finally the frequencies and mode shapes. So if you consider the highest frequency mode, so that will be corresponding to smallest time period, because no, your time period is 2 pi by omega n. So if you look at the time period, so that is going to be the smallest time period, and this actually depends on that. So of course there are methods to further estimate this. So this delta t critical is typically given by t n, let me just write, divided by pi, where this Tn is the smallest natural time period, or no, natural means free vibration basically. So the Tn is the smallest natural period of the system under consideration, and usually this number can be very small. So Tn is the smallest natural period of the system under consideration. And since this is the highest, corresponding to the highest frequency, usually highest frequencies are very, very high. So Tn is going to be very small. So if Tn is small, means your delta t critical is going to be small. That means you have to choose a much smaller delta t. So if you are choosing a much smaller delta t, so then what it implies in terms of solution, that I have to finally, starting at t equal to 0, let's say I have to reach up to maybe, let us say 1000 seconds. I am just giving as an example. So I have to reach there, but since my delta t has to be something of the order of microseconds, maybe few microseconds, because the system under consideration has got smallest time period of the order of microseconds. So this delta t is also in terms of microseconds. So then you have to discretize this into a large number of time steps. So you will end up solving this equation for a large number of times, even though from the accuracy point of view that small delta t may not be needed. So you have to then choose judiciously whether you want to go for the explicit numerical integration scheme or implicit. Now we suppose we were interested in something where this time is not this, but it is something of the order of, let's say, 10 to the power minus 5 seconds, that is 10 microseconds. And then my delta t also from the stability point of view of the method also is of the order of same. So number of steps required would be less. So if you are modeling a phenomena which is something, the time duration involved is of the order of say few microseconds, and your delta t for the given system is also minimum delta t coming out to be of that order. So then it might be useful, because then you are not doing in the solution of simultaneous equations here. We use with the consistent the lumped mass matrix, and then the solution can be faster. But if it is something of this order, which is typically the case in case of structural vibrations. Structural vibrations are usually the vibrations in lower frequency mode, so the time period involved is more, and which would be of this order. Sometimes even it can be more than this, and then usually you don't prefer this method, but you actually prefer implicit methods which are unconditionally stable. So that means there is no restriction from the stability point of view on the choice of delta t. So it's only governed by accuracy, and from the accuracy point of view, that delta t turns out to be much larger than what you get from the stability point of view in case of explicit methods. So the next, of course, know about all this. You want to read more, best description you can find is in the finite elements a book by K.J. Bathe. So there is a chapter on dynamic analysis, numerical techniques. So you can read that. So there are a lot more details about stability. Even based on these equations, you can set up an eigenvalue problem, and using this equation and similar other equations, you can set up an eigenvalue problem. You can actually estimate that when you try to find out the eigenvalues of the resulting system, they must be less than 1, so that the errors do not get amplified. So all that, if somebody wants to do a more detailed reading, you can actually refer to finite element by Bathe. So the next next set of the methods are implicit time integration, so implicit time integration techniques. So main thing here, as we had said in case of explicit, that equation of motion is considered at time t to find solution at t plus delta t. in case of implicit schemes, what we are doing, the equation of motion is considered at time t plus delta t to obtain solution at t plus delta t. Whereas in case of explicit we had said we write actually or consider the equation of motion at time t to get the solution at t plus delta t. Here we are writing the equation of motion at the same instant at which we want to find out actually the solution. So that means when I am looking at the equation of motion to find the solution at t plus delta t, I will consider this equation of motion m at d double dot at t plus delta t plus c at again d dot at t plus delta t and plus k and then again d at t plus delta t is equal to right hand side force also at t plus delta t. Earlier we were writing everywhere t here. So although this is a linear problem, so all these are constant, m, c and k, they are constant. But in case of nonlinear problem, you will find that this k itself is going to be now function of unknown displacement, say d at t plus delta t. So then the solution becomes more complex in case of implicit techniques. But on the other hand, when you look at the explicit, so even if let us say k is a nonlinear function, that it depends on the unknowns, but since the equation of motion there is considered at time t and you have already got the solution at that time instant, so you can easily evaluate your the stiffness matrix which is dependent on the displacement, and then from that you are working out the solution for the next time instant, that t d at t plus delta t. But here the solution becomes more complex in case of nonlinear problems, because the equation of motion is considered at this time instant, and if this is function of this unknown, so then this is also not actually a known quantity. So then you need the iterative solution. So for example, Newton-Raphson method, and there can be a convergence issues and so on. So that needs to be done. So that is a drawback which comes with this for the nonlinear problems. Now what we are doing, as I said earlier, that since we are looking at the numerical solutions, so this is your starting point t equals 0, delta t, 2 delta t and so on, and then you would have got somewhere t minus delta t, then t and t plus delta t, and then you continue. So again, since this is a discrete solution, we need two more equations, because there are three unknowns, this vector and this vector. So we need two more equations, and depending on how we construct those equations, so there are different again implicit techniques for particularly the second order systems. So the one is known as Newmark method. Newmark's method, and in this also there are usually two variations. One is known as average acceleration, that is what I will discuss, average acceleration version, and linear. I will explain you what is the meaning of these terms. So there and this is most popular for structural dynamics. This is what you use. So this is known as Newmark's. There are other. One is known as Wilson theta. They are actually more or less Wilson theta method. And there is a third. As I said, this is most common. Third is known as Houbold. And if you actually appropriately program, you can by changing certain parameters, you can actually either degenerate that to this or to this or this. So these are typically three methods for this integration of this equation, Newmark's, Wilson theta and Houbold. Again, average acceleration. So what I am going to discuss is this Newmark's average acceleration. Technique. So what you are doing here, that let us see, if I look at this side the acceleration vector, I mean it's a schematic representation. So if I look at d dot at any time, so what we are assuming that no, I am here at t and then I want to go from t to t plus delta t. Obviously at this instant you would have some acceleration which is say d double dot at t, and then at this point you will have some acceleration, one can be smaller or larger than the other. So this is d double dot at t plus delta t, that is acceleration value here, acceleration value here. In between it will have some variation, although we are not trying to find that out because we are interested in finding the solution here and here. So in this average acceleration method, what is assumed is that the acceleration between t to t plus delta t is average of the acceleration at t and delta t. So what we assume that the acceleration from here to here, that is this is the average acceleration, which will obviously be given as half of d double dot at t plus d double dot at t plus delta t. So this method is known as average acceleration method. So this is your average acceleration. Now once we assume that between t to t plus delta t acceleration is average, so we can write the velocity vector at time t plus delta t in terms of average acceleration and the quantities known at t, and we can also write the displacement vector using the same kind of formula which you, is there any doubt? So if you want to write the now assuming this as an acceleration, so v is equal to same kinematics you would have done this equation, v is equal to u plus at, same kind of equation here. So if I want to write now d dot at t plus delta t, I am not, these are all vector quantities, but I think every time putting the curly bracket takes more time. So this d dot at t plus delta t would be equal to d dot at t, so that is initial velocity vector, so d dot at t and plus acceleration times delta t. So acceleration is average acceleration, so that means, and delta t is delta t, so delta t by 2, and then this here we will have d double dot at t and plus d double dot at t plus delta t. So this is simply I am assuming that the acceleration between these two time instances t and t plus delta t is constant given by average of the acceleration here and here, since we would have got the solution up to this point. So actually we know this, but this is still an unknown. So we are still writing this velocity vector at time t plus delta t in terms of unknown acceleration vector at time t plus delta t, that is d double dot at t plus delta t. So this is the velocity. So now this is one more equation relating these variables d dot at t plus delta t, d double dot at t plus delta t, and the quantities at time t, velocity and acceleration. So similarly I can write d at t plus delta t in terms of these quantities. So it's like s equal to ut plus half a t square. So this will have initial some value of d, so d at t plus now ut, and u means initial velocity, so that would be delta t into dt dot and plus half of at square. So half means half of the average acceleration, and so you get at means t is here delta t, so delta t square, and 1 by 2 because of average and another by 2 because half at square, so you get 4, and then here you will have d double dot at t plus d double dot at t plus delta t. So this is like initial s naught plus u into t, so this is like your u, this is t, and this this plus this divided by 2 is your a, so half at square, so this is delta t square, half and 1 half because of average acceleration, so you get 1 by 4. So now see, in addition to this equation of motion, now we have got two more equation, and the same thing is done in all these, whether you take Wilson theta or linear acceleration or average acceleration, what we did right now, and also the Hobart method, you construct these kind of equations, additional equations, and now once you have number of equations equal to number of unknowns, you can solve this. So now typically what we do is from these two equations, we express d dot at t plus delta t and d double dot at t plus delta t in terms of one unknown, that is displacement at t plus delta t, and of course the other quantities at t. So first what you can do is, for example, from this equation, the last equation, you can write d double dot at t plus delta t in terms of this and rest of these quantities. So if you do that, see finally you find that It's a straightforward, no, you take this also to the left hand side and this also to the left hand side and then divide it by delta t square by 4 and then take this also to the left hand side. So that is what you get. So from this equation finally you can write that d double dot at t plus delta t, this will be equal to, so let me write quickly here. So this comes out as 4 by delta t square and into d at t plus delta t minus d at t. So that's the one term, which is nothing but, no, you are taking this to the left hand side and then dividing by this. So this is what you will get, and then the other term is then what you will have is this divided by delta t by 4. So you will actually get 4 by delta t into d dot at t. So this is one term you will get, and then finally this term which is minus dt double dot. So now what we did, just we have rewritten this equation, no. You are writing d double dot at t plus delta t in terms of d, which is an unknown, and d at t which is known, d dot at t which is known, and d double dot at t which is known. So in terms of this unknown and rest of the known quantities we have expressed this. Now then what we can do is we can put, no, whatever we got here into this equation, and we can express d dot at t plus delta t in terms of d at t plus delta t and rest of the quantities at basically time t. So similarly from this equation you can also write that, no, d dot at t plus delta t would be, you are just going to substitute, no, this here and then just rewrite, no, collect the same kind of terms together. So you finally find that this comes out as simple expression, which is d at t plus delta t minus d at t and minus d t dot. So this is what is the expression for d double dot in terms of this unknown and d dot again in terms of unknown displacement at time t plus delta t. Now you substitute these, let us say that this is equation A and this is equation B. You substitute this in the equation of motion, that is the initial equation I wrote here, this equation. So if you substitute here and finally, no, take all the known quantities to the right and the unknown quantities to the left. So your equation of motion at, and see this is always you are doing in all the numerical techniques, whatever, no, I said Hubble and Wilson theta, the similar, only thing is the form of these expressions, this equation and this is going to change. The coefficient of, no, this coefficient would change, this coefficient would change, this coefficient would change, but the form would remain same. So it's a similar kind of a logic. So now equation of motion can be written as by substituting these two and collecting all the unknowns left and all the known quantities to the right. What you will have is, you understand, no, so you are going to put this into the equation of motion m into d t plus delta t double dot. So in terms of unknown you will have m into 4 by delta t square. So the left hand side I will have 4 by delta t square into m, because this is only unknown in d double dot t, then this term will go with c into d dot at t plus delta t, and in terms of unknown this is only 2 by delta t. So you will have 2 by delta t, you can actually try yourself, plus k of course as it is there in the equation, and then here I will have d at t plus delta t, and this is equal to, then the right hand side you have of course f at t plus delta t, external force which was there, and then no, this part of, no, the inertia terms coming from this term, this term, this term, they will go to the right hand side. So you will have from here plus no, m times and then all of these. So you have here d at t to the right side plus 4 upon delta t into d dot at t and plus d double dot at t. So this is from the inertia term, and then these two terms from the damping will also go. So plus you will have again c, and here this is 2 by delta t into d at t, and of course this is as it is, so minus d dot at t. So this is the final equation you will get. Now see this equation, if you look at this, you see that it involves, when you are trying to solve this problem, again let me explain you that here I have t minus delta t, I have t here and t plus delta t, I have already got the solution up to this, and then we are looking for the solution at this point. So now as you see here from this equation, that the solution at t plus delta t, that is actually this, depends on the right side what we have, d at t, d dot at t, and d double dot at t. So that means the solution here only depends on the values of displacement velocity and acceleration vectors at t, not at t minus delta t, whereas in the explicit case central difference, that was also requiring the value of d at t minus delta t, and that is why special is starting condition. So when we start the solution at t equal to 0 and then say go to delta t, so I only need the conditions here which are coming from your initial conditions, and from the equation of motion at t equal to 0 you can work out the acceleration. So everything is available to start this. So there is no special starting procedure needed for this implicit technique. The another observation you will see that now if you look at this coefficient matrix of unknown vector d at t plus delta t. So earlier it was involving only mass and damping, and if damping is negligible then it is only in terms of mass in case of central difference, and that can be diagonalized using lambda approach. Whereas in this case, because k is also coming in implicit technique and k cannot be diagonalized, so that means we always have to solve set of simultaneous equations, because there is a coupling, k is not a diagonal matrix. So all of this, even if you use lumped diagonal mass matrix and damping is negligible, because of this k, this is again going to be a coupled system. So we always need to find out inverse of this matrix, multiply to the right hand side, then only we will get this solution. Inverse means there are different techniques, I am just referring in terms of solution. So that's the drawback here, because it requires solution of simultaneous equations. So that means if you have something like if you are trying to solve a very large size problem, where maybe your total degrees of freedom in the discretization might be 2 lakh, 3 lakh, even maybe 5 lakh, 10 lakh. So that means you can think of you have to solve those 10 lakhs equations or 5 lakh equations simultaneously. Although they would be banded and sparse system, but still you have to solve them simultaneously. So a lot of time goes in actually getting the inverse of this matrix. Inverse means equivalently the solution of the equation. Again, for linear problem, it's actually not an issue, because this is subsequently if you keep your delta t constant, then this whole thing is going to remain constant. So once you set up this matrix and invert it and store that inverted form, and then you keep on using that, only you will keep changing, recalculating your right hand side. But if you are again, although we have not included here nonlinearities, but if this system is nonlinear, then every time instant this the left hand side coefficient matrix is going to change. So you have to form it, you have to invert it, and so a lot of time goes into doing that. So that's the price which we pay here in terms of solving this. We need to solve this set of simultaneous equations. But the advantage is in case of implicit techniques. So the implicit techniques are unconditionally stable, at least for the linear problems. For non-linear problems there can be some stability issue. Linear problems, and what it means is that we can choose delta t only based on the accuracy requirement. So now how you choose this delta t typically now in structural dynamics. See you would do say first free vibration analysis, and you also know what kind of forces are acting on the structure. So roughly the frequency content of the forces are known. So then you would know that what is the possibility of, or what is the highest mode which can actually get excited and participate in the response of the structure. So then whatever is the highest mode participating in the response of the structure, so then you choose, at least if I look at the response of highest mode participating in the structure. So let us say that it will have that mode will have some response like this, and its time period is going to be this is the maximum time period you are going to minimum time period here, because this is the highest frequency mode. So the time period is going to be maximum. So this is going to be T max, time period. So then delta T roughly you can choose T max divided by, typically what we do is about 20 if you choose for linear problems, this would be sufficient. Then what you are basically saying that I should have at least, to correctly represent this waveform, I should have at least 20 points like this here, so that I can accurately represent this waveform. But this is based on the what is the maximum time period not max, sorry, I'm sorry, this is minimum time period. So it's the highest mode, frequency is maximum and time period is minimum. So because it's governed by that, I'm sorry. So this is T min. Highest frequency, smallest time period. Highest frequency means it is not the highest frequency of the discretization, but highest frequency of the mode which is expected to participate in the response. So even though let's say we will have let's say a 1 lakh degrees of freedom system, that is after discretization we have 1 lakh unknowns in the problem. So obviously we will have 1 lakh pre-vibration frequencies and corresponding mode shapes. But we are not interested in all those 1 lakh modes, but maybe the first 10 or 20 modes. So what I am talking about is T minimum is of, let's say, the 20th mode, which is the mode predominantly participating in the response. So modes up to 1, 2, 3 up to 20, they are participating in the response. 20th mode is the one which is having the smallest time period. So T min divided by 20, you decide your delta T, so that your waveform would be represented accurately. In any case, for all other lower modes having higher time period, you will have more number of points in one cycle of all other modes lower than this. So your response just delta T is governed by this. And this you will find, as I was saying, it can be much larger than what is needed in case of explicit techniques from the stability point of view. So if typically if you see that structural dynamics problems, we actually use implicit techniques. So although we will have to solve this set of simultaneous equations, but since we have larger delta T and the time duration involved is more, so we are ultimately ending up solving say let's say here whatever the minimum time period, within that we are having 20 points. So if there are 100 let's say cycles, we have to solve this problem. So this is 20 into 100, 2000 times you will be solving these equations. But the same problem if you wanted to solve using let us say explicit technique, then this delta T would has to be much smaller. Although from the accuracy point of view, correctly representing the response, the time variation of the response, you need only this as the delta T. So then we don't mind solving the simultaneous equations lesser number of times than solving the problem much larger number of times in case of particularly structural dynamics problems where time involved is of the order of few hundred seconds. But you use explicit where the time involved is of the order of microseconds, which is obviously of the order of delta T required for the stability of the numerical technique. So that is the kind of trade-off you do. Of course, if you are handling nonlinear problems, so this can be larger than can be delta T can be further smaller. So for example, whatever nonlinear dynamics problems I solve, periodic response and so on. So we typically choose this T max by around 200. So for all nonlinear problems I have been working on from a research point of view, my students. So we typically take this T minimum by 100 or 200, and that is good enough for to get the accurate solution for even nonlinear problems. But linear problem, this 20 itself might be enough. And why of course, if you choose delta T smaller than that, your solution is going to be accurate. But then if you are choosing delta T smaller than this, then unnecessarily you would be solving the equations even at intermediate time instances. So then your computational time is increasing. So finally you have to reach up to some time, maximum time of the response study. You would be reaching to that with more computational time, because you are solving these equations at more number of time instances, which is otherwise not required from the accuracy point of view. So this is actually what I wanted to discuss on the numerical integration techniques. Now so far whatever we have seen, everywhere finally we need to solve the set of simultaneous equations. So then there are different techniques. So I'm just going to give you a brief introduction, maybe today and maybe the next class. So solution of simultaneous equations, which is needed in whether you are doing static problems or you are doing dynamic problems, solution of simultaneous equations is needed. So now what are the different methods? Basically, finally, even if you look at the dynamic problem I was talking about here, finally no, this is one matrix into this unknown is equal to right hand side. So you will always be solving some equation of this form, say I'll say A or whatever name you give, A into say unknown D is equal to something you have on the right side R. So this form of the equations you are always going to solve, whether it's a static problem, equilibrium problem or a dynamic problem. Even when you are doing eigenvalue solution, then also you need similar kind of solution of simultaneous equation. And typically, because we are not talking about 2-3 equations, as I was saying, you can have 1 lakh, 2 lakh, 5 lakh degrees of freedom. So here you are talking about solution of that many number of equations. So you need efficient solution techniques. So in general, if you look at the methods which you would have studied, so I think all of you must have done this Gauss elimination. I am not going to know if you have forgotten, you can actually refer to in any book and look at this. So one is Gauss elimination method. So this is we keep in assume that there are no round off errors, then this is actually accurate solution of simultaneous equations. We are trying to solve them accurately. And then there are iterative solution techniques. So for example, which you would have learned is Gauss-Seidel iteration. So you all know these two methods, right? Gauss elimination and Gauss-Seidel iteration. And then the other methods we typically use is, one is known as LU decomposition or Cholesky factorization. So let me, I think I will discuss about Cholesky. Cholesky factorization method. You can also have ELU decomposition, LDU decomposition, so there are various versions of this. And you also have say maybe in optimization you study a technique called conjugate gradient method. Again, this is for solving the set of simultaneous equations. So essentially solution of this kind of equation is equivalent to minimization, and of course in here we can, for most of the problem we can write the integral functional, and that integral functional solution of finally resulting equation is equivalent to minimizing an integral functional, the way we wrote. So you can use this conjugate gradient method. And then you also have what is known as frontal solution technique. And then for large size systems nowadays packages have another technique known as GEMRES, which is actually essentially the improved version of this. So GEMRES meaning is generalized. So first G is coming from this generalized minimum residual. So the first two letters and then this M and then first three letters. So that is how GEMRES. So these are some of the techniques. So I am not going to discuss this. I am not going to discuss this. You can look at this. I will discuss some of these. So if I look at the Cholesky factorization, so for example, I am going to just conclude here. So what you are doing is, I will only briefly discuss this and then continue in the next class. So in Cholesky factorization, what you do is that you have your A matrix, and matrix A you are writing as the product of two lower triangular matrix. So that is L transpose into L, and where L is, A is a full matrix, but L is, if I look at L, and depending on the size of the system, the number of rows and columns, of course these are square matrices. So L is going to be, first row is like L11, and then rest of the things are 0 here, and then you start here L21, L22, and then 0, 0, and everything 0 there. Then the third row is like L31, L32, L33, 0, and so on, and like that that is how your L is defined. So if we decompose a matrix A as a product of L transpose into L, where L is a lower diagonal matrix, we call this decomposition as Cholesky factorization, L transpose into L. And now if you look at the solution first, so what we have to get is, we know this matrix. Based on this, first we will have to find out this L, means L1, L2, L22, L31, L32 and so on. Once we know this, then finally we look at the solution of the equation. So solution of the equation, original set of equation is A into D is equal to R, and then A you are writing as no L transpose into L into this D is equal to R. And then what you are doing here, see now it is what you do actually is somewhat similar to what you do in Gauss elimination essentially. So you transform the in Gauss elimination method, no lower diagonal you make it lower half below the main diagonal you make it 0. Same thing you are actually doing here, just only difference is that here no the whole matrix itself is written as product of these two. So first what I can do is, no I can solve for this product. So let this L into D be equal to, no, so let this is equal to some y, let me say. So this is equal to y. So my resulting equation will transform to L transpose into y is equal to R. So first I will solve for y from this equation, and once I have solved for y, then I will finally get this D. So now see, if you look at L transpose, particularly the structure of this equation itself, if you look at, so the L transpose, the way I had written here, so now L transpose is going to be like no, L11 here, L21, L31 and so on, it will go like that, and then this will be you will have 0, and then you will have L22, L32 and so on. You follow, no? Just I am writing the transpose of this. So then you will have 0, 0 and then you have L33 and you will continue, and finally now if you look at the last row here, so the last row will be like all 0, 0, 0 till end. Finally we will have here some, let us say L N N, and rest of the things will be 0 in that equation. This is your L transpose into y is like, no, let us say y1, y2, yn. Before this you will have something like here, no, you will have like this is L n minus 1, n minus 1. So you will have one non-zero term here, one non-zero term here, and this is equal to, of course, right hand side R1, R2, and this is Rn. So in this what you can do is, first you start with the yn, because now from this equation first I can write yn is equal to Rn divided by Lnn. Once I have got no yn, then I can work out yn minus 1, because no then yn minus 1 would be in terms of already this known quantity. So that is going to be, no, like as per this, the previous subscript is going to be no L n minus 1 n minus 1 into y. This is what I am going to get. So I am sorry, I am writing little, I know you understand what I am trying to say. So then yn minus 1 would be written in terms of in the numerator what you are going to have is Rn minus 1 minus Ln minus 1 n into yn and divided by Ln minus 1 n minus 1. You can think of, no, so the last equation is solved first, then next equation like this. So this step is known as back substitution. So this is what you call as back substitution. So once you have got this, but see the advantage here is, no, simply you are dividing. So Rn divided by Ln, and then no yn minus 1 is Rn minus 1, that is next right hand side here, minus no this term into yn is taken to the right side again, so that is what is written here, divided by this term here, which is a diagonal term, and then you keep solving. So you get yn minus 1 and up to finally y1, and once you get y vector y, then you again come back to this equation. Now when you look at back this equation, that is L into D is equal to y, And if you look at the L, the way we have written, this is L11 0 0 and so on, then you have L21 L22 0 0 and so on, and all this into here. What you have finally is D1 D2 Dn, all the n degrees of freedom is equal to y1 y2 up to yn. So first you will now evaluate D1, because D1 would be simply y1 divided by L11. Once you have evaluated that, then D2 would be y2 minus L21 into D1 divided by L22. So this is known as forward substitution. And at the end of this, you get the solution. Okay. So this is known as Cholesky factorization. We have not discussed how to get this basically L matrix, but given L matrix, this is what by first backward substitution and then forward substitution will give you the final solution. So this is known as Cholesky factorization approach. The others I am going to discuss is this conjugate gradient for frontal solution technique. So these are the two more techniques I will discuss after talking about the Cholesky factorization. You want to read more, you can, for some of these you can refer to book by Bathe, and for GEMRES you can refer to book by Saad or maybe actually journal papers. So we will continue in the next class. If you have any doubts and questions, you can ask outside.